Okay, now we're going to start with our chapter 7, which is Eigenvalue Problem. So the problem here is we need to find eigenvalue in the matrix. Okay, we want to find eigenvalue or scalars for which there exists a non-zero vector v such that this equation AV equals to eigenvalue v. This is the eigenvalue, alright, and this is the eigenvector. Okay, so let's say if we have 2 by 2, we will have lambda 1, lambda 2. So we will have eigenvalue 1, eigenvalue 2, and we also will have our vector eigenvector 1 and eigenvector 2. 3 by 3, we will have 3 lambda 1, 2, 3, which is eigenvalue 1, eigenvalue 2, eigenvalue 3, and we will have eigenvector 1, eigenvector 2, and eigenvector 3. 1, eigenvector 2, and eigenvector 3. It is in pairs. Right, if you look at your slides, you will see this equation. Okay, so actually A is a matrix 2 by 2. So if you have 2 by 2 matrix, you will have lambda 1 and lambda 2, two eigenvalue. And then you need to solve this equation, okay, A minus eigenvalue identity. So you will get this matrix here. In order to find the value of the eigen, okay, you need to find the determinant using this equation. So you will get lambda squared minus 8 lambda plus 13. Using direct method, you can solve it directly by solving this polynomial. As you can see, for 2 by 2 is quite easy to solve. But if you have 3 by 3, 4 by 4 matrix, it will become much more harder, much harder. Okay. So instead, we will use numerical method to solve this polynomial, to solve this, to finding the eigenvalue instead of directly solving it. Okay. This is the 3 by 3 matrix. So as you can see, for 3 by 3 matrix, we will have 3 eigen 1, eigen 2, and eigen 3. So in this space here, right? 3 type of eigen. Now, if you try to solve it directly, again, like I mentioned before, you find the determinant of this matrix here, so you will get the polynomial. And you can directly solve the polynomial to find the eigen, but it will get harder each of as higher the number of matrix, 4 by 4, 5 by 5. So it's become a problem to solve directly the polynomial. So in this chapter, we will solve it using numerical method, as I mentioned before, by using what we call as a power method. Before we go to the power method, there is one theorem that we need to discuss on eigenvalues. This theorem will show the characteristic of the eigenvalues. Let's say we have a matrix here. Let's say it's a 3 by 3 matrix. Alright, the lambda, let's say for 3 by 3 we have 3 lambda, lambda 1 plus lambda 2 plus lambda 3. It is actually, it's the sum of value of the middle, A11, A22, A33. It is equal to the sum of these three. Lambda is equals to lambda 1, lambda 2, lambda 3 is equals to A11 plus A22 plus A33. Equals to A11 plus A22 plus A33. This is the characteristic for the eigenvalues. This is the characteristic here. And if we multiply them, it will equals to the determinant of the matrix. Usually, when we want to solve a real-world problem, we want to know where the initial value of the eigenvalues in the plane. Because when we want to apply numerical methods, we need to have the initial value, so we need to know where it is located usually. This is where the Gershgorin circle theorems come, where it can help us find the spots where the eigenvalues will be in the plane, where it is located in the plane. Okay, this is the mathematical equation for the Gershgorin circle theorem, but I think it's better for us to go through the example to see where you can see directly and clearly how to find the location of your eigenvalues. Okay, let's see the first example here. We have matrix A, which is a 3 by 3 matrix. So we know that if we have 3 by 3 matrix, we will have 3 eigenvalue position. All right, for the first one, second one, and the third one, we have 3 eigenvalue position. Okay, we will solve the example row by row. So we start with row 1. So row 1, we have 3, negative 2, and 1. All right, so as I mentioned before, the important thing here is this value here in the middle, A11, A22, A33. In this theorem, the middle, let's say 3 in A11 here is 3, A22 here is 3, A33 is negative 4, will be the center of the circle. All right, let me show you. So you use the formula given in the previous slides, where we will have lambda minus 3. 3 here comes from your A11, okay, for the first row, and then negative 2 plus 1 is for the 2 other position here, and this is absolute, means that negative here will become positive. Okay, so 2 plus 1 will be 3. This will be your radius, this will be your center. So what do we have? Let's say you can draw this. Okay, you can have that 0, then you can have negative 1, and so on, negative 2, negative 3. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Okay, as this is absolute, so the one here that we want to plus and minus. So 3 here, the middle 3, plus and minus the radius. So you will get, this is the center, 3. If you plus 3, you will get 6. If you minus 3, you will get 0. And then you can make one circle. Okay, so this is 3, this is 3, the radius, all of it is 3. Okay, this is what this equation means. So the lambda is in 0, 6, between 0, 6 here. Okay, this is how you solve. You try to solve using this theorem. You try to find the location of the eigen. Okay, so again, this is the center. The center for row 1 is A11 here. The center for row 2 will be, after this we will calculate A22. The center for row 3 will be the A33 value. And then the other two will be the radius. And then you plus minus the radius with the center. So you will get 3, because the radius is 3. 3 plus 3 is 6. 3 minus 3 is 0. So you will get the lambda is inside 0 and 6, the eigenvalue. This is how you draw the circle for row 1 that I already tried to draw before. Okay, this is where you get your 3. This is the center. Remember, our center is 3 before, based from the matrix 1 1, and then we have radius 3. So we have 3 plus 3 and 3 minus 3. Okay, because of the plus minus of the radius. So we get 3 minus 3 is 0, 3 plus 3 is 6. So this is the circle of the row 1 here that we already calculate. Finish with row 1. We calculate and already draw the circle for row 1. Now we're going to start with our row 2. Here is our row 2 where this will be the middle 3. Okay, A11, A22 and A33. So these two you must plus because this is absolute, so 1 plus 1. So the radius will be 2. Okay, we select our row 2 and then this will be the equation for this theorem. So this will be middle, and 1 plus 1 negative 1 will become 1. 1 plus 1 is 2. This is your radius. So 3 plus minus 2, 3 plus 2 will be 5. 3 minus 2 will be 1. So for this the answer is the eigenvalue is inside 1 and 5. And again after this we will draw the circle for our row 2. Again center here for row 2, remember the center is A22, so this is the center and this is the radius, negative 1 plus 1, negative 1 plus 1, this is the radius. So you will get your center and radius. Then you can draw the circle. Same here, only X line here, there is no Y, only X. Okay, then you have your middle here, which is the center, which is 3 based from our metric, and then our radius is 2 plus minus 2. So the circle will be, the eigenvalue will be 3 plus 2 is 5 and 3 minus 2 is 1. Alright, then we move to our last row, row number 3, where this will be our middle, A33, our center, and we plus 1 and negative 2 to become our radius, and it is absolute, so you can say 2 plus 1, which is 3. 3 will be our radius for row 3. Same again, select row 3 and then use the equation given. Okay, so we have our center is negative 4 and our radius 1 plus negative 2, which is absolute, then 1 plus 2. So our radius is 3. Okay, this is our center, negative 4, and 1 plus negative 2, which is 2, 1 plus 2. Alright, absolute 1 plus 2 is equal to 3, which is our radius. Then again, we plot the circle, okay, for our row 3. Negative 4, this is the center based from our metric A33 there. Then the radius is 3, so negative 4 plus 3 will be negative 1, negative 4 minus 3 will be negative 7. So negative 1 here, 4 minus negative 4 plus 3, negative 1, negative 4 minus 3, negative 7. So this is the radius. The last step here is to combine all the 3 circles that we have done, okay, based on our row. So we will have the first one here, the first one, the second one, and the third one. And if you combine these 3, you will get a huge one, the circle, one dimension here, from negative 7 to 6. Okay, this is where the eigenvalue is located. This is the range of the eigenvalue. Okay, this is what this theorem can help us find the range of the eigen. This theorem can help us roughly estimate the value of the eigen, where it is between this range that we have here, negative 7, 6. But we do not know the exact location of the eigen, exact value of the eigen. We just know the range of the eigen, that it is between negative 7 and 6 based from this theorem. So if you want to proceed to find a more precise value of eigen, then we will use our power method here, which will give us a more accurate value of our eigen here. As you can see here, the power method is an iterative technique, so it is quite the same because this is numerical method, right? It's the same as your chapter 6, where it is iterative. You need to do again and again and again until the error where you can stop. Okay. By modifying the method slightly, it can be used to determine other eigenvalues. Okay, so one useful feature of the power method, it produces not only eigenvalue, but you also can find the associated eigenvector using the power method. If here lambda 1, you know, if you 3 by 3, you have 2 by 2, you will have 2 lambda, lambda 1, lambda 2. If you have 3 by 3, you know that we will have 3 lambda, lambda 1, lambda 2, lambda 3. Okay. So if lambda 1 is an eigenvalue of A that's larger in absolute value than any other eigenvalue, it is called the dominant eigenvalue. An eigenvector V1 corresponding to the lambda 1 here is called a dominant eigenvector. As I mentioned before, to apply power method, we assume that the n by n, 2 by 2, 3 by 3 matrix has the eigenvalue equivalent to the n here. It's 2 by 2, 2 eigen, 3 by 3, 3 eigen. Okay, with associated collection of linearly independent eigenvectors. We assume that A has precisely one eigenvalue, lambda 1, that is largest in magnitude, so that lambda 1 is bigger than lambda 2, or big, and then lambda 2 is bigger or equal to lambda 3, and so on. Okay, so lambda 1 is the biggest here. The power method formula actually is quite simple, where you need to use this here from this and then find this equation here, and then after you find this equation, you will use this iteratively. So again and again and again, that's all. You put into the equation and then you can find the answer. Okay, so this is where it is repeated. You need to repeat this again and again until it satisfies the error or you get your answer. And then to start the power method, you need to have initial value, which is a vector here. We call it vector iteration 0. Okay, this is not vector 0, this is vector iteration 0. Initial vector here, initial value here in vector here cannot be a vector 0 because this is a multiplication. So let's say you have matrix A here, and then you multiply by the first vector, vector 0, and if the vector 0 is the vector initial value here is vector 0, which is this one, you will have 0. All of it is 0 because this is multiply here, multiply, and then this also multiply, so you will get 0. You cannot have the first initial vector is a vector 0. Initial vector must be other than vector 0. Okay, so don't be confused. V0 is not vector 0, it is initial vector, the first vector, okay, that must have value other than 0. Okay, this is what I mentioned before, that you need to do this sequence recursively again and again until you find the answer. Okay, that I will explain later in the example. Okay, what is the termination criteria? Same as chapter 6, we have a termination criteria to stop the recursive, to do the recursive sequences. Okay, the termination criteria here is where we have the v here, the vector here, minus the previous vector, and it is less than our error that we have set. Okay, as mentioned before in chapter 6, we know we have our error. So if it is less than the error, then you know you can stop the calculation. This is standard in numerical method, where we need to have an error, okay, because we need to know when to stop. So in numerical method, where we estimate the value, so we set the error, we need to have the error, the accuracy, okay, for our answer, and then if it's less than the accuracy or the error that we have set, then we can stop our calculation. This is the vector and the distance between the vector here. Okay, vk plus 1 minus vk. How to calculate the distance between the vector? I think we already covered in our chapter 2. Let's look at our example. So the example, our problem should have a matrix because we want to solve eigenvalue in matrix. Okay, we want to find the eigenvalue in matrix, so we need to have a matrix in order for us to start. Okay, doesn't matter the size, whether it is 2 by 2, 3 by 3, and so on. Okay, doesn't matter the size. So, but we need to have the matrix. Then we need to have the initial value of our question here. The initial value, initial vector. That is not a vector 0. Okay, it is not a vector 0. You cannot have all zeros, as I mentioned before. But we need to have our initial vector. We can choose any value except our vector 0. That's important, okay? The initial vector depends on us, okay, and it will affect our how many iteration that we need to do. And then we also need our error as our stopping criteria. Sometimes they will give this in form of decimal points. Accuracy, decimal points, how many? And then you must know from that accuracy that they want, the decimal point, you must know what is the error that they want. That should be for the accuracy for the decimal point that they state in the question. The calculation also, if let's say here they give you 3 decimal points, so your calculations for the question here should be in 3 decimal points also, in order for you to be able to find the error, to be able to satisfy the error. This is the same as in our chapter 6. 3 decimal points, calculation in 3 decimal points too. Okay. The first step when we want to solve this problem is to find the v. Okay, so we have our a, the vector, the matrix, and then our starting value, starting vector here. The initial value of the vector is v0. Okay, so you multiply them and you get your v. Alright. The second step is based from the v here that we find the largest value here, the largest absolute value that we can find. So here we have -1, 1, 1. So of course, the largest value here is 5, the absolute value. Okay. So we select here 5, the largest magnitude, the largest absolute value, as our M1. Alright. Largest magnitude here means, as I mentioned before, the absolute value. Okay. Let's say we have the answer for this one is -6. So if -6, 1, and 5, our M1 will be here 6. Okay, because it is absolute. Absolute means that no, it's not based on sign. It is based on the magnitude. So this will be our M1. Okay, if this one is not -1, this is -6. Okay, but in this case, it is straightforward. -1, 1, 5. So 5 is the largest magnitude. So we choose M1 is 5. The next step is we need to use the vector here and divide by our M1. So divide by our M1. This vector divide by our M1, which is 5. Right here, 1/5 here, and -1, this is the vector. So you will get a new vector, which is our vector 1 here. Alright. If you can see these two is based from our previous formula for this power method here that I mentioned before. Okay, that we need to use recursively, reiteratively. Okay, where we find our next v1, and then if it is not satisfied the error, so we find our v2. Again, if not satisfied, we find our v3 using the same thing that we do here. Find the vector first, and then you find the next one. Okay, we do it again and again. Then we need to check for the iteration. So we have our v1 here, right? And we minus with our v0 before, and then see whether it is less or not than our error, which is 0.001. But this one is much bigger, so we need to do our next iteration, which we need to find our v2. Then we go to our next iteration where we find our v2. And first thing here, this one is already v1, okay, based on our last calculation. So this is our a, this is our v1, and you will get your v. So based from these three, choose the highest magnitude. Okay, so for this question, of course, negative 0.8, 0.8, and 3.4. 3.4 is the one that we choose. Okay, and okay, I give another example here. Sometimes students also make mistake here. Okay, let's say I have negative 3.4. This is the answer. Okay, between negative 0.8, 0.8 and negative 3.4, which magnitude is bigger? So if you look here, if you want to choose the magnitude, choose the one that is the biggest, regardless of the sign. Okay, regardless of the sign, is 3.4 is the biggest. Alright, even though it is negative 3.4, of course, if you look at the sign, negative 0.8, negative 3.4. So the biggest is 0.8 if you're looking at the sign. But if you just look at the magnitude, the biggest is 0.8, 0.8, 3.4. Of course, it is 3.4 is the biggest. Okay, if you are not looking at the sign, that's the magnitude, the absolute value. But when you want to choose, let's say you choose negative 3.4 here, it should be you take everything including the minus, not just 3.4. Okay, you take including m2 is equals to negative 3.4, not just the magnitude. The magnitude is which you want to choose, either this one, or this one. That is when you disregard the minus here, when you want to choose which one. But after you have chosen 3.4 is the biggest one, you drag it to the m2 with the sign. Okay, two different things here. Choosing, how to choose based on the magnitude without the sign. Okay, so 3.4. But where you want to take that to your m2, you take that along with the negative sign. So m2 is equal to negative 3.4. Okay, and then you bring the negative 3.4 into the equation below. 1 over negative 3.4. Okay, multiply by the v. Alright, this is sometimes students make mistake here, where they just take 3.4. They don't take the negative with them. Alright, just use the magnitude for choosing, and then after you have chosen that, you use it with you take it with the negative also. Okay, this is for the example if you have negative 3.4 here. But of course, our question here is not, the answer is not negative 3.4, so it's that straightforward. So the biggest magnitude is 3.4, so you take 3.4 as our m2. Okay, because this is the scenario only. Okay, this is not for this question. Don't mistaken what I say here. This is just a scenario if it is negative. But for this question, it is not negative. It is positive 3.4. So the largest magnitude of course is 3.4, so the answer is 3.4 straight away. Okay, but I just want to be clear with this procedure. Okay, then after we get our M2, do the calculation. Alright, so this is your V, so you will get your V2. This is your M2. Okay, so you get your V2 and then find your next iteration, whether V2 minus V1 less than our 0.001, but for this iteration it is not, so you continue to the next iteration, finding your V3. Now as you can see here, usually in the exams, we do the first two, you do the workaround for the first two iteration. Okay, you do the workaround as I mentioned in the previous slide here. Do the workaround for the first two, and then 3 and so on, 3, 4, 5, you can just fill up this table. Okay, this applies to for our chapter 6, where for numerical method in chapter 6 you also do the workaround for the first two. Okay, do the calculation, everything, show me the calculation for the first iteration and the second iteration, and then the third, the fourth, the fifth, the sixth, until you find the answer. You can put it in the table, just put the value in the table. Okay, you don't need to show all the work until, let's say here until 7, you don't need to show all the work like the previous slide until 7. Okay, you do the first two, the first three, the first two I think is enough. You do the first two, so you let me know that you know how to calculate. You know how to calculate chapter 6 and chapter 7, the numerical method. You know how to do the iterative. Okay, and then because it is iterative, it will be the same until number 3, number 4, number 5, number 6, 7th iteration. That's why show the first two to show us, the examiner, that you know how to calculate, and then fill up the rest in the table. Please remember this in your exam for numerical methods. Okay, back to the example. Alright, this is your the initial value, the V0. This is the V. Okay, when you multiply, this is the V. This is the M, M1, M2, M3, M4, and so on. The second row here is your V1, and then this is your V. Okay, after you multiply, and then this is your M1 based from the first iteration here. M2, sorry, this is M1, M2, M3, M4, and so on. As you can see, this is the same as chapter 6, where it is quite easy, but it is iterative, so you may fatigue if you want to write everything from the first iteration until the last iteration, and you can make mistake during the iteration process. Okay, but the thing to solve is quite easy, but the iterative thing that will make you make mistake in your calculation. If you look closely, the M here, it will go and converge at one point. Much smaller, 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 and converge at one point. If you see the V here, almost inseparable here. If you minus, the error will be very, very small. Okay, so this is where to find the error. So what's the answer? The answer is the M here that we got. For this question is the 3. This is the answer that we want to find. So when we want to show the solution, okay, so you say that V7 here, which is this one, minus V6, which is this one, less than our error, which is less than 0.001. Remember our error previously? So V7 minus V6, you get less than 0.001, so you can stop. So you can say that the eigenvalue is the M here, the last M here, so M7, which is 3. This is your eigenvalue, and this here is your eigenvector, which equals to V7. The V1 is equals to the V iteration of 7, the 7 iteration here, which is negative 0.25, 0.25, and 1. This is your eigenvector. So remember, you will have two answers. okay, two things, one answer but two things. One is your eigenvalue, okay, based from the last m, which is this one is m7, and the eigenvector, which is the last iteration here for our v, which is also v7, and you will have your eigenvector with your eigenvalue. Alright, so we have two values here. As I mentioned before, if you look closely at power method, they say that they will find, if you use power method, you will find the most dominant value of your eigen. Okay, so here if you can see, we have matrix 3 by 3, right? So we have lambda 1, lambda 2, eigenvalue 3. So eigenvalue 1, eigenvalue 2, eigenvalue 3. So using power method, you will find your eigenvalue 1. So the most dominant one. Okay, this is the most dominant eigenvalue here. So it is approximately 3. Okay, and the V1 here is actually the pair. Every eigenvalue will have the pair. Okay, so this one is V1, V2, V3. This is the pair of their eigenvector. So this is your eigenvalue 1, which is the most dominant, and this is your eigenvector for eigenvalue 1. Okay, so this is the answer that you get for using power method. Okay, you get the most dominant eigenvalue with its pair of eigenvector. Then when you get your answer, you can check back whether it is true or not by applying the equation that at the start of our power method here. So you have your A, so this is your V1, right? So equals to, this is your lambda 1 and this is your V1. If you can get it the same, remember our error is very small, 0.001, so usually we get it the same, similar, very similar. Or if the error is quite large, maybe you have quite difference here, 0.75, let's say 751 is 752, so quite just a bit different, so you can accept it based on the error. Okay, but usually if our error is very small, like 3 decimal here, 0.001, 0.005, very small error, so you get the estimate here is the same, the estimation is the same between these two, so you can say that your answer is correct. The next one, we have the shifted power method. So this can be done by modifying the power method as it is. By subtracting a scalar from both sides of the standard eigenvalue problem, the eigenvalue of the matrix are shifted. Okay, so you can write it as A shifted V, lambda shifted V. Alright. By shifting the power method, we can find another value of the eigenvalue. Let's say we have matrix A, okay, matrix A, and then we minus it by a scalar, we shifted it by a scalar, which let's say S, and this is matrix A, this is our scalar S, and this is our identity matrix. Depends on the this one depends on the matrix. This 2 by 2, so the identity will be 2 by 2. Is 3 by 3, the identity will be 3 by 3. So if we shift the matrix here, matrix A minus the shifted value here. So if you can imagine, we already draw before, right? So if we shift this, it will only shift the middle part here. Okay, the center part here. If you notice before, when we draw, let's say this is our circle, the radius does not change. Okay, if we shifted the matrix A minus the scalar here, it will shift only the center. The radius is still the same. Let's say here is the radius. Okay, so if we shift here, let's say the center is here, so it will be the same. It will be the same as the same radius that they have, okay, but different places. So this is what we say as shifting the matrix. By using this characteristic, we can find another value of the eigenvalues, okay, by doing the shifted power method. This is what it means by shifting. We shift the power, the matrix, but the radius is still the same, because we just change the middle here, the identity matrix here, the middle here. Shifting of eigenvalues of a matrix can be used to find the opposite extreme eigenvalue, which is either the smallest magnitude eigenvalue, the smallest of the magnitude, or the largest magnitude eigenvalue of opposite sign. Okay. For example, for the smallest magnitude eigenvalue here, if you have all the eigenvalue, the magnitude of the eigenvalue here is in the same, which is all positive or all negative, the largest we can find here is 8 here, right? And the smallest is 1. So if you are using the shifted power method, you can find the eigenvalue for the smallest one here, which is 1. Okay, this is the smallest one, right? All positive, in this case all positive, so this is the smallest one. If all negative, you can also find the smallest magnitude also. Remember, this is the smallest magnitude. Magnitude is the smallest number, okay? But if you have plus and minus, okay, so you can find, by using the shifted power method, you can find the largest magnitude eigenvalue of opposite sign. So we have opposite sign here, which is -2 and -1, right? So shifted power method can find the largest magnitude eigenvalue of opposite sign. So is this -1 or -2? It is -2. By using the shifted power method, you can find -2 because the magnitude is the biggest compared to -1. Magnitude is 2, right? Compared to 1. So you can find the largest magnitude, which is -2. It is different between these two. This is for, the first one is for the same positive or the same negative, okay? But for the second one, the largest magnitude that you can find of the opposite sign. In this case, -1, -2, so the answer will be that you can find is -2, the largest opposite sign. Okay, to show the example on why we got what we have in the previous slide, consider a matrix. So we have a consideration of a matrix whose eigenvalues are all the same sign, which is here all positive. Okay, this is to prove the previous slide. Let's say we have an eigenvalue of 1, 2, 4, and 8. Right? So eigenvalue 8 is here is the eigenvalue of largest magnitude. Okay. If you want to find the largest magnitude here, you can use our power method. If you remember, our power method is to find the largest magnitude of the eigen, right? But the eigenvalue 1 is the opposite extreme eigenvalue. Okay, so the eigenvalue of largest magnitude lambda 1 here equals to 8 can be found by the power method. So you use power method, you can find 8 as your answer, as your eigen, right? The eigenvalue of largest magnitude here, you can find this using the power method that we have done before. So the shifting here, when we do the shifting of the eigenvalues by, let's say 8, let's say the S here, the scalar, remember what we have done before, the equation here, A minus Si, right? So when we have done this equation, we will get our shifted metric B. We call it shifted metric B. This is after the shifting here. So let's say our S here is 8. Okay. So when we shift the eigenvalues, we minus 8 for, let's say, 1 minus 8, 2 minus 8, 4 minus 8, and 8 minus 8. Okay. When we minus 8, you will get 1 minus 8 is negative 7, 2 minus 8 is negative 6, 4 minus 8, negative 4, 8 minus 8 is 0. Right. So if you look here, based from this, which is the magnitude is the largest magnitude here? Which one is the largest magnitude after we minus 8? As I mentioned before, magnitude is not about the sign, it's about the numbers. So 7 here is the biggest magnitude, right? So actually, if you do matrix B here after the shifting, which we have done here, we minus 8, so we have got our B. The matrix here will find the largest eigenvalue, which is 7. You will find this 7 here. And if you see 7 here is what? It is actually finding the smallest, the opposite extreme value, which is 1. 8 now is 0 and the largest one is 1. So by doing this shifted power method, we can find the opposite of the extreme eigenvalue. Power method, you will find 8, the largest one. Shifted power method, you will find the extreme opposite, 1 here, which is the smallest one. Okay, so this is why if we do the shifted power method, we can find the extreme eigenvalue, the opposite extreme eigenvalue compared to our largest. In this case, it is 1, because when we minus the scalar here, we find out that the smallest value is the smallest value in 1 here, we will get negative 7, which will have biggest the biggest value among the metric B. Okay, so we will found two types of eigenvalue, the highest and the lowest. As I mentioned previously, the largest magnitude eigenvalue of the shifted matrix, metric B before, the largest magnitude eigenvalue of the shifted matrix can be found by the power method lambda shifted largest, which is negative 7. We have discussed this in the previous slide. And if you can see, the smallest eigenvalue of the original metric may be found by lambda smallest equals to lambda shifted largest plus 8, because this is the scalar, remember? So negative 7 here plus 8 equals to 1, which is the smallest eigenvalue in metric A. Okay, so if you remember, lambda 1 is 8. This we found by using the power method. And if you are using shifted power method, okay, you will get the value of the lowest eigen, which is shifted power method 1. Okay, if you do the previous one, power method, you will get the largest one, which is lambda 1. If you remember, lambda 1 bigger than lambda 2, bigger than lambda 3, bigger than lambda 4. If you remember the previous 3-4 slides. So the largest one is lambda 1, which is 8. And then the smallest one is lambda 4, which is 1. You can find the largest one using power method, and you can find lambda for the smallest one using the shifted power method. Alright, When we have a matrix whose eigenvalues have both positive and negative, like here we have negative 1, negative 2, 4 and 8. So we have some negative and some positive. So the 8 here is eigenvalue of largest magnitude, and 2, negative 2 is the opposite extreme eigenvalue. Okay, in the opposite, the highest extreme eigenvalue for negative 1, negative 2 here, because this is 8, the negative 1, 2 is the opposite extreme eigenvalue. So the eigenvalue of largest magnitude, lambda 1 here, you can find it using your power method that we have done before. If you shift by s equals to 8, okay, so if we shift this one by 8, negative 1, minus 8, negative 9, negative 2, minus 8, negative 10, 4 minus 8, negative 4, 8 minus 8 is 0. So if you shift the eigenvalues by 8, it yields the shifted eigenvalues, negative 9, negative 10, negative 4, and 0. Okay, so same as previous slide here, minus 8 is our S, right? 8 and identity matrix, and you will get your B, metric B. Then in metric B you will have this eigenvalue here. So which one is the highest magnitude based from the metric B here, the eigenvalues? It is 10, right? So actually 10 here is what? In the matrix, in the A here, in the eigenvalue of A, it is the value of negative 2. So it is not the smallest value of magnitude. You will find, if you have plus and minus sign for the eigenvalues, if you do the shifted power method, you will find the opposite extreme eigenvalue, which is, we have 8, so the opposite is negative, right? So the extreme, the highest one is 2, because we have negative 1, negative 2. So we will find, if you do shifted power method, you will find the eigenvalue for negative 2 here. Okay, before this you find the smallest one if you have just one sign, either negative or positive, but if you have both, you will find the opposite extreme eigenvalue. If you can see here, if you shift it by 8, negative 1 is negative 9, negative 2 minus 8, negative 10. So we will find the eigenvalue, we will use the highest magnitude, which is negative 10. If you refer back, this negative 10 will be the value for our negative 2 in matrix A. Don't be confused of this, okay? As I mentioned before, the largest magnitude eigenvalue of the shifted matrix can be found by the power method. The lambda shifted largest, which is the largest that we found, is negative 10 based on our previous calculation. The largest magnitude eigenvalue of opposite sign of the original matrix may be found by, so the lambda of the largest negative, the eigen of the largest and negative, is equals to the shifted largest plus 8. So the largest is 10 plus 8, negative 10 plus 8 is negative 2. So this is the largest magnitude eigenvalue of opposite sign. How to do the shifted power method? Okay, to summarize, first you need to have the largest magnitude lambda 1. You need to have the largest magnitude lambda 1 using the power method. So basically this usually will be given to you, the lambda 1, the largest magnitude will be given to you, okay, because the largest magnitude we will use as our S shifted here, okay, it is used for our shifted, the lambda 1. So example, this is the matrix, right, minus lambda 1 identity matrix equals to for here they use A shifted, but it's up to you, for you can use B, doesn't matter, okay. So this one is just to show you that we already shifted, A shifted, metric A shifted. So you can use A shifted if you want. But, or you can just use another name. For me, I use B. So you need to have this first in order to find the matrix, the shifted one, right? So this one usually will be given to you in the exam or in the equation, or you must calculate this first. Let's say you must calculate the largest magnitude first using the power method, and then use the lambda 1 that you have found, the eigenvalue that you have found for the shifted power method. Okay, so you must have this, and then you must shift the matrix A by S, which is equals to the lambda 1 that you have found in the first one here. So you do this equation, so we get this matrix. Okay, and then solve the eigenvalue of the lambda shifted by the power method. So solve this using the power method that you have learned before. Same thing, same equation, same iteration. Okay, the only difference here, you shift it first. Don't do it on here. This is not the matrix A. Do it the power method on the matrix B that you have found after you have shifted the matrix. Okay, and then after you have got your power method there, you solve the number 3. You must compute the opposite extreme eigenvalue of matrix A by finding the eigenvalue equals to eigenvalue shifted plus S. So from this, the answer, you must plus back your S, the eigenvalue. Okay, plus your eigenvalue with S, which is your previous lambda 1 that you have found here. You must plus back again to get the answer. So we have 4 steps. 1, 2, step 3, step 4. Step 1 depends on the question. Sometimes you need to solve this first using the power method in order to find the largest magnitude, the lambda 1, or it will be given to you by the question. Then you must use number 2 here to find the shifted matrix. Solve it using the same way that you solve for power method, and then you must plus back again with your S, the lambda 1 that you have found before. Okay, let's look at the example. We have a matrix here, matrix A, 3 by 3 matrix. So if you remember, the first, we have 4 steps before, right? So the first step is to find the lambda 1, the S, okay, the dominant eigenvalue. For this question, they already give to you lambda 1 is 3.0, so you already know your lambda is 3. Okay, no need to find it. This question, they give it to you already. And then use the shifted power method to find the remaining eigenvalues of A. So then we can go to our second step, which is using the equation to find our B. For example, this is your A, right? Minus, this is your S, the lambda 1, right? This is your identity matrix. Okay? Because this is identity matrix, the one that will change is only in the A11, A22, A33, in the middle only. Okay, if you see here, this one is the only one that's changed, this 3, based on your S here, your lambda 1. The others remaining the same. If you see here, these 3 and these 3, same. There's no change. The only one change, because this is a matrix identity, right? The only one that is changed is on the middle only. Okay, based from your lambda 1 that you have found. Okay. Then we continue with our third step. Right, then same as before, in step 3, give you the V initial, which is 010 here, and your error is 0.001. So what you need to do here, this is your matrix, right? The matrix B that we have calculated before. This is your initial value, the vector initial value, and then this is your V that you have found. Okay, so based from these 3, same thing, we look at the magnitude. The magnitude here, the biggest is 4 regarding the sign. So you take this 4 as your M1, but you take it wholly. including the negative. Okay, as I mentioned in the previous example. You have your M1 that we calculated before, which is -4, and your V is your previous vector you have found, right? And then when you divide it, you will get this answer. So this is your V1, and you minus your V initial and see whether it is less than error or not. So far, based from your observation, it will not. Based on our observation, V1 minus V0, it will be not less than our error, which is 0.001. So no. So we need to do the next iteration to find our V2. Then you will find your answer like this in the table. As I mentioned before, you do the first two, show me the work for your first two iteration. Okay, then the next one, the next iteration, you can just put it in the table. Alright, so it will save you time for me to understand what you have done. It's enough by using the first and two iteration. The next one, just put the result in the table. So as you can see, where it is less than 0.001, here you can find V10 minus V9 here. Okay, so at this part we know that our error is 0.001. So when you minus them, V10 minus V9, it is less than 0.001, so we can stop, right? And the answer will be -2. Our M is -2. This is the one that we want to take, and then this is the eigenvalue -2, and then this is the eigenvector -0.5, 0.5, and 1. But this is not the final answer yet. We have the last part, if you remember, where we need to plus again our S, our lambda 1. Okay. As I mentioned, based from our table before, we have our eigen shifted, which is M10 is equal to -2.0. This is eigenvalue. And then the eigenvector is -0.5, 0.5, and 1.0. But the last step that we need to do in shifted power method is to plus back our eigen shifted with our eigenvalue of the biggest eigenvalue that we found, the lambda 1 before that we have shifted. Okay, which is, this is the value of our eigenvalue of the shifted one, and this is the lambda 1 or the S, the shifted that we have done in the second step. Okay, so when you plus them, you will -2.0 plus 3, you will have your answer. The lambda for the shifted power, the lambda for this question, the answer is 1.0. This is the eigenvalue for this question. Okay, don't forget to do this last step. Sometimes students forget to plus again the shifted value that we have minus before. Okay, but the eigenvector is still the same. We just take from the answer here, -0.5, 0.5, and 1.0, still the same. The one that's changed only, we need to plus back with our lambda 1 or the S, the scalar, is the eigenvalue. So this is the answer for the eigenvalue 1.0, and this is the answer for the eigenvector, which is -0.5, 0.5, and 1.0. Then you can check back your answer whether to see whether it is correct or not by using this equation. So this is your A, this is your V, and then this is your lambda that we have found for this question, and this is also your V. So you should get the same here like this, or it is okay if you have maybe very small differences. Let's say this is 1.501, maybe this is 1.502. Okay, it's quite similar, right? Because this is almost the same, so we can accept that too if the error is quite small. Okay, since the opposite extreme eigenvalue that we have found is 1 and has the same sign as the largest magnitude eigenvalue of the original metric, which is 3, right? So this is the largest that we have found, this is the smallest, the opposite extreme eigenvalue that I have found. All eigenvalues of metric A are positive and eigenvalue equals to 1 is the smallest eigenvalue of matrix. Remember, we have 3 by 3 matrix before, right? So we have found our lambda 1 equals to 3. We have found our lambda 3, which is the smallest one, which is 1. Right? So we also can find our lambda 2. Okay, based from these two. We have found our lambda 1, the biggest one. We have found the largest, the opposite extreme eigenvalue, which is 1, and we can find our lambda 2. How to find the lambda 2 here, right? Because we know we have 3 by 3, so we should have lambda 1, lambda 2, and lambda 3. We already find our lambda 1, which is the biggest one, right? And then it's bigger than lambda 2 and bigger than lambda 3. We have found our lambda 3, which is 1. So how to find this? If you remember, we have equation where lambda 1 plus lambda 2 plus lambda 3 is equals to our 3 by 3 matrix A11 plus A22 plus A33. So we have our lambda 1 already, 3 plus, we don't know, plus 1. If you look back at our matrix, A11 is 1 plus 0 plus 5. A33 is 5. So equals to, this is 6, 6, 3, 1, 4 minus 4. So the lambda 2 will be 2. Okay, so we have found our lambda 1, 3, lambda 2, 2, lambda 1, 1. Bigger than previous one. Lambda 1 bigger than lambda 2, bigger than lambda 1. Lambda 3, so lambda 1 bigger than lambda 2, bigger than lambda 3 here. Okay. But we only find the eigenvalue, which is 2. We cannot find the v2. We still cannot find the v2. Okay, we can only find the eigenvalue of the middle one, the lambda 2. But we cannot find the vector, the eigenvector. This is same as what I mentioned to you before, right? So how to find the intermediate, the middle one, the immediate eigenvalue, which is lambda 2. Okay, so we have your equation here. And then you know that we have our lambda 1, lambda 3, and you know this A from our matrix. And you can find your lambda 2, your eigenvalue 2, the middle eigenvalue. But you cannot find the V2, just the eigenvalue.